Hello. Celso Batalha, Astro 10, Astronomy Online, and let me go over a few points in Chapter 3. And so, Chapter 3 is the chapter that has a lot of physics and also is a transition between traditional astronomy, kind of old fashioned astronomy up to Kepler, and modern astronomy that is started with the onset of Newton's law of motion and Galilei experimentation and the way science as we know got organized nowadays. So there are two aspects of chapter 3 that I need you to put your attention on. The first is the three laws of Kepler that govern the motion of planetary objects in our solar system. And Kepler, Johann Kepler, basically, he found these laws using a lot of observations done by Tycho Brahe, but also trying to match and creating mathematical models that could reproduce the observations. Now, there is not a theory supporting Kepler's law. The theory came after Kepler itself, and that came through the hands of Isaac Newton in his theory of gravitation. So these two laws is what I would probably emphasize in chapter 3. So let's go through those two aspects. So Copernicus, up to Copernicus, and based on the fact, as we discussed in chapter 2, if you look at sky objects, they seem to be orbiting ourselves, orbiting Earth. It was not difficult for ancient astronomers to establish Earth at the center of our universe and have everything else going about. And that led to Ptolemy model of the universe, Earth in the center and the planets pretty much stuck in spheres going around Earth at different rates. And the last sphere was the sphere, the celestial one, where the stars should be. And they would, at different paces, they would be orbiting Earth at the very center. Now, Copernicus gave a different view, and he presented a mathematical model in which the sun was in the center of the solar system and planets would go around the sun in circular orbits. Now, based on comparing observations with model, which means prediction, what the planet should be, and what the model, what the observations really would give, there was some discrepancy, and Copernicus still used the artifice of placing these planets going in circular orbits around deference. So the epicycle was still going on. So it was not an ideal model, but the major difference between Copernicus and Ptolemy model was the shift from having Earth in the center of the solar system to the sun as being the center of solar system. All these models, they have some fudges because we observed planets undergoing what we call retrograde motion. What is a retrograde motion? Let me see if I can pull up in my planetary. And again, I would try to be a little bit more specific when we study this. We study this in our chat room, and I try to have a dialogue with all of you. So this is a sky. Where is this? Oh my God, 2022. So let's go 2017. Okay. So in June 30th, what today is today? So let's go August. Let's go July, August. let's go to, I don't know what the, September, September 7, 7, September 7, oops. There you go. So let's say in September 7, 2017, the sun will be at 2:45 p.m. The sun is going to be in the constellation of um, Leo. It's going to be there in Leo. Okay, very good. So I'm putting as label Mars, Mercury, and Venus, and Jupiter. So you can see them right there, right? So Jupiter, Mars, Mercury, and Venus. So if I go one day ahead, see what happened? The sun goes from west, which is right hand side, to east, left hand side. But also the planets. See Venus go west, go to the east. Mercury goes to the east, and Jupiter goes east as well. So let's keep doing this. Now the moon is coming. The moon always go eastward. And this type of motion is called prograde. So I'm advancing one day at a time. So I'm not speeding up the time in a second or minutes basis, right? If I do that, you would see all these objects slowly progressing from the eastern sky to the western sky. What I'm doing is facing a sky region as if I were not connected to Earth, and then I see what happened with the planets as I observe these fixed sky objects in a very far away, and I'm moving about one day at a time. So if I keep doing this, um, the planets they keep moving with the sun towards east, and we call this prograde motion. Oh, I think I choose it. Oh, look at Mercury. Okay, look at Mercury right here. So Mercury is going eastward as well, but now, let me see. Venus, nothing happened. They are all prograde. Jupiter's prograding, Venus is prograding, Mars prograding, Jupiter's keep. Oh, look at Mercury. See Mercury right there in the left-hand corner? Okay, wait a second. I'm gonna advance. I'm gonna move the time a little bit. Okay, so close your eyes. Okay, December 13, 2017 at 8:24 a.m. The sun is about to rise. Of course, I have a, this should be the case, right? But I'm getting rid of daylight. Um, get rid of daylight. Okay. So planets and the sun and the moon, they all move most of the time. In fact, the sun and the moon all the time from the western sky to the eastern sky in respect to the stars in the background. This is not daily or diurnal motion. It's in respect to the star in the background. But look what happened with Mercury. See Mercury over there? It's passing Venus going to the western sky. So Mercury is retrograding. This is called retrogradation, when the planet uh, get rid of its normal motion and now it progrades. And with respect to the background stars, goes from the eastern sky to the western sky. And Jupiter is prograding, the moon is prograding, Mars is prograding, all right. Mars keeps prograding, Jupiter's, oh, look at Jupiter. I think Jupiter will start retrograding. So it stopped, and now it's retrograding, see that? I don't know if this clicking is making too much of a sound. I hope not. So retrograde motion. So let's go back to the slide. Retrograde motion is the apparent motion of planets in respect to the background stars from east to west. And in order to explain retrograde motion, both Copernicus and Ptolemy first, they had to invent these epicycles. So epicycles mean the planets, instead of going on a flat circular orbit around Earth as they thought, or in case of Copernicus, planets going a circular orbit around the sun, they had to go in a circular orbit around another circular path called deferent. And then as they go in a circle around the deferent, sometimes um, they go forward, which means from west to east, as most of the times they do, but sometimes they have to go around and retrograde. Now Kepler came after and present his three laws of motion. The first one is that the path is not a circular path. This is very important. The planetary path is called ellipses. And ellipses are curves that have two foci. And in one of the foci, in the case of our solar system, the sun is located. There is nothing in the other foci. So an ellipse is divided or is crossed by two major lines called semi-major axes. So there are semi-minor axes. So in this figure right here, the minor axis runs in a vertical line and the major axis run in a horizontal line. And there are different types of ellipses. In fact, planets go around the sun in elliptical orbit as determined by Kepler's first law, but the ellipse is not as elongated as it is or as they are for, let's say, comets. Comets do have an elongated orbit, and we name that type of elongation eccentricity. So they are pretty much eccentric orbits. So the orbits of planets around the sun, they seem to be almost circular, but they are not perfectly circular. And there are some off, as this picture attempts to show. The second law of Kepler is a little bit more subtle. And that is, if you take a line connecting the planets to the sun, that line will sweep out equal areas in equal amount of time. So if you take the area in red and the green and the blue, the areas are the same. So think about areas as is a surface, is a measure of how large the surface is. Think about it, if you can place black beans and fill these areas or these regions with black beans, the amount of black beans in the green, blue, and red shall be the same. So the areas are the same. But you see the path, the orbital path in the red area is much bigger than it is in the green area. So Kepler's second law determined that if the areas are the same, and in this figure they are supposed to be the same, then the time it takes the planets to cover the path, the time should be the same. So what is the consequence of it? So the consequence is, if you look at this red path, because it's bigger, then the time, as being the same, require the speed of the planet at this red path. It has to be much larger than it is in the path associated with the green area, right? Because the path is less. So you have to cover that in the same amount of time. So you have a certain time to cover just a small fraction of that sector, whereas in the red one, it's a bigger one. So you have to go faster. So as the planet go around the sun and gets closer to the sun, it speeds up, and as it's further out with respect to the sun, the average speed is less. That is the second law of Kepler, sometimes called or named the law of equal areas representing equal amount of time in which the planets have to cover. But the main consequence is when a planet is closer to the sun, it should go faster than it is when it's further out. The third law of Kepler is a mathematical law that relates average distance of planets to the sun with the orbital period, the time they take planets to go around the sun. It's usually presented with an expression p, or the period square, is equal to the semi-major axis, which is the average distance of planets to the sun to the third power. So P2 is equal A3. A is usually a letter representing the semi-major axis. So we don't have a lot of mathematics in our course, is more descriptive, but you might find some of these relations in your homework. If you have any questions, you can always drop me an email. P2 is equal A3. So what's the consequence of it? If the planet is further out, like Jupiter, for instance, the period, the time it takes this planet to complete a whole sidereal orbit around the sun, the time is much larger than it is for, let's say, Earth, which means Jupiter goes at a lower pace, at a smaller speed than Earth does. So Mercury, for being the closest one, is the one that has the shortest period, the one that goes faster around the sun. Now, the three laws of Kepler came without a theory underlying. They are more empirical in the sense that you observe things and collect data, and then you fit a mathematical expression that fits the data. So it's amazing that P2 is equal A3 works well for the solar system. There is no explanation. And in science nowadays, if you have an empirical law, you must be able to explain why this law exists. You have to produce some educated explanation to that. And so you could say that Kepler is somebody that lies in that interface between old science and the way science is dealt nowadays. So you cannot just come up with any empirical law without trying to explain why the mathematics is the way it is. So Newton came afterwards in the 1700s and proposed his three laws of motions. We studied those laws in physics, and in our course, what I would like to call your attention is the mathematical expression that gives rise to this law, and here it is. The gravity force. And what forces are? Forces are quantities or qualities of nature that are able to change the motion of things. For instance, I have a cup of coffee in front of me on the table. So I have to exert a force on this cup in order to change its state of motion, which is not moving right now, right? So if I want to move this coffee, hopefully to my mouth, I have to grab it and I have to exert some force on it, and I have to overcome its tendency to stay there forever. If you have a car going in a straight line in a constant velocity, to change the direction of the car, you have to exert a force on the car so that this change in direction, change in velocity might occur. So we learned that in physics, but for us in astronomy, gravity is a name used in association with not only formation of stars, but also formation of galaxies, these majestic, complex systems of hundreds of billions of stars. So gravity is a force that keeps all this entity together and controls the dynamics and the interaction of these different parts. For instance, in chapter 1, we mentioned the local group of galaxies consisting of a few dozens of members. So this local group of galaxies held together by a force. What's the name of this force? Gravity. So gravity keeps them together. They don't fly away and take their own path because they are bound. They are held together. So what you need to know about gravity? So gravity, the force, the intensity, the magnitude of it, depends on a constant, which is this letter capital G. 6.67 10 to minus 11 is a very small constant, but it's also uh, given by the product of the mass of the two objects you are considering. For instance, take Earth and the Moon. Moon is attached to Earth because of gravity force, as well as Earth is attached to the Moon. So the force between those two objects depends on the product of both Earth mass and Moon mass. So you have to have those two quantities, certain amount, in fact, a big amount of kilograms, and then plug those numbers in this equation to figure what's the intensity of force that hold them together. But that is also divided by r square. Square means that you are multiplying r twice, and is in the denominator. And r is the distance between those two objects, not their surface, but from their center of mass, center of gravity. So that is what gravity force is a force that depends on the product of mass and inversely proportional to the square of the distance between those two objects. So take, for instance, Earth and the Moon. They are at certain distance. So if you move the Moon away from Earth than it is now, the gravity force between those two objects will fall down because r is in the denominator. Or for some stranger's reason, the Moon gets fatter. You get more mass in the Moon than it is right now. I don't know. It could be the Moon collide with some big asteroids. Who knows? It can't be. But let's say if for some strange reason one of these two members, Earth or Moon, become more massive, then the gravity force between them will grow. In fact, I have one of the discussions is I ask you to play with these two factors. There is an applet, and I would like to see your opinion on it. That's the gravity force, and in this diagram here, you have in green the direction of gravity force, because if you think about the cannonball and planet Earth itself, there is a line connect the center of gravity of the cannonball and the center of gravity of Earth. And as the cannonball moves around, and especially if it's far away, see, it's in the third display, it's kind of a curving around because and the green line is kind of a going an angle because Earth is curving too. So the direction of gravity force is towards the center of Earth. So what this diagram is indicating is that there is a speed in which the cannonball can be released. And again, you have to imagine this situation occurring in case there is no air resistance at all, because as the cannonball moves through the atmosphere, collides with air molecules, and then these air molecules creates a force, a drag resistance that slows down the motion of the cannonball. So imagine there is no atmosphere at all. So under this situation, there is a speed that once you release the cannonball, there is a speed the cannonball you just be following towards Earth, but never exactly touch the ground, because it's curving at the same rate Earth is. So unless it meets a mountain or something or a tree, it's just keep on going around Earth forever. And this is what our book calls circular velocities, that velocity just right to keep an object in orbit. And that brings one of the important points in this chapter, and that is, well, the Moon is always falling towards Earth, as this cannonball is, but never touch the ground because the speed is just right to keep on going. It has some rotation, some revolution, as we say, or angular momentum, if you want to be more specific, that brings the Moon into this full rotation and never really touch the ground. In fact, because of the gravitational interaction between Moon and Earth, in fact, the Moon is not following, it is moving away 3/4 of an inch a year as a result of transfer of angular momentum that is caused by frictional dissipation of continents and oceans on Earth, and which is a topic which I think we're going to be discussed in a future chapter. And pretty much that's it. And I hope to see you in the chat room. In this chapter, we review these two aspects of chapter 3, Kepler's law. You must have a good understanding of the three laws of Kepler and Newton's gravitational law, specifically what gravity is. And we are going to be repeating gravity on and on and on in future chapters.